They're selling houses.
We out here selling
This
products.
is a $2 house, right? $1 house. This house was free, right? It was.
Jay takes
it's
a
our
free
tent.
house, you take the $1 house, and you can kill.
That's the which scenario?
This is photoelectric. This is photoelectric. Jay's the tent. That's right.
Magic sense.
All right.
It goes down. Like she moves down, he moves down.
Okay, so let's see. So now we have, let's say that we have an X-ray photon coming in.
Yes.
Right, so this is interactions of the X-ray photon inside the body, right? So these are all electrons inside your body, all part of a single atom.
Right.
And along comes an X-ray photon, right? Let's say that, all right, there you go. All right. So if you're an X-ray photon, where would you be able to move into? With the amount of money you have.
How much money you have on your card?
So how much money do you have right now? Show everyone.
Just $1.
Great, you've got $1. So where can you move in? Great, you could move in there. Where else could you move in?
Free.
In the middle as well, right? So you can move into those side two. But can you move into where Emily is? No, right? You do not have enough money. You do not have enough energy. But since we are dealing with photoelectric, I'll go ahead and give you some more. Here you go.
Okay.
Right?
How much money does she have?
All right, and then,
Oh.
all right, so
So these are the electrons inside the atom.
electrons inside the atom. Yep, these are our electrons.
So they're meaning the 3 or there might be more electrons
In fact, here,
inside.
you know what? Take one more. Okay, so these are the electrons inside the atom inside our body. Along comes Melanie, who is our X-ray photon, and she is going to come and try and buy up the most expensive house here. So, come on, right? So she walks over to the atom.
You have to strike
She
her.
says, "All right, got some money here."
There you go.
Right. So you're gonna end up giving all your money to Emily, right? So not only do you give her the $2, but you give her a little bit extra just as a
Profit.
tip, a bonus.
The profit, right? So
You
then
know,
only.
to get her out of here faster,
Uh-huh.
right? You get an extra bonus if you
I
if
can
you move right now, right?
release them.
Don't take 2 weeks, right? Just get out now. Okay, so that happens. What happens to Melanie's energy?
Zeros.
0.
Yeah.
Remember, what is a photon?
Photon is a particle with energy.
Right, a photon is a particle of energy. So if there's no more energy left, do we have a photon left?
No.
No, so Melanie has disappeared. Right, so vanish over this way. All right, so our photon has vanished, right? Photon came in, photon disappeared.
Right.
This electron on the inside now has a bunch of money, bunch of energy, right?
Yeah.
So what's the electron gonna do?
Getting out.
That's right, they're like, all right, thanks guys, I'm out, have a good one. Peace, right? And our electron wanders off.
Yes.
So now, there's this nice house for sale, correct?
Right.
So what did it, when she goes away, because she gives away the energy to the electron, the electron has energy, so it's wandering now because there's electron. That's what you said?
Say that one more time.
Yeah, when the electron got the energy,
Mhm.
so now it wants to wander off because it has the energy to do things. That's what
Right,
you said.
mhm, right, so our photon paid the electron enough energy to make the electron leave.
Okay, right.
So, now, we've got 2 more electrons here. They're both eyeing this really nice beachfront property now. And so, electron over here comes over and it's like, hey,
Sorry.
I want to buy this, right?
I'll move that.
Want to buy that? All right, great. Our electron wants to buy it. So, in order to buy this, you need to give me some money, right? So, here, let me start you off with some money as well, right? Here, have some money.
Bullet.
All right, so in order to move in, the electron needs to spend some money. And you've already got a $1 house, but you want a $2 house.
Oh, you have to upgrade your.
So that's right. Electron wants to upgrade, so you're going to pay to upgrade. All right, great. I need someone to carry this money since I don't have hands right
So
now.
my question is, what's the benefit of upgrading?
Hmm?
Why would you want to upgrade?
It makes them feel safer.
That's,
More comfortable.
why does the
It's more
electron want to
comfortable.
upgrade them?
So,
Remove
for example,
the shell.
Or they can't be kicked out from the thing. Oh,
for
I
example,
see.
if I have a stack of books, right? And I pull out the bottom book, are all the other books just gonna stay there? No,
Yes.
they're gonna fall down, right?
Oh, I see.
Same thing here,
It's a chain.
right? If I take out the electron, all these now wanna fall down into the lower spot.
So she doesn't have to buy, so she'll go volunteer automatically.
Well, she has to pay some energy. She has to, so
Oh, I see.
she takes this energy, right?
I see.
So now, we've got a particle of energy again, right? What do we call this?
The scatter.
That's the
Oh,
X-ray.
no, this is not.
That's the X-ray photon.
This is a photon. This is our secondary photon.
Oh, I see.
Okay? Now, you get to move in. Yay! Nice upgrade.
Congratulations.
Alright, well now we've got this, oh, hold on. Now we've got this new house that's available, right? Right, Jay wants to move in now. Right, once again, gotta pay up. So, no, different photon. Different photon needs to carry this energy. Right, so, you hand it off to your attendant, your other photon, to help carry the money to the bank, right? And so now, he's moved in to this lower area, right? So, come over here, you're not living here for free.
Where's she coming from, sir?
So now we've got two photons that were created, right? Two secondary photons created because they each moved down by one level. Now we still have a level 3 over here, right? So if we did have another wandering electron, right? So Emily, if you want to stand back up, you can put your money down, you don't have. Right, so now we've got this poor electron that's just wandering around, right, looking for a home. And do you notice, hey, there's a free spot, right? And so it would jump in and finish filling up the atom. And so the atom is right back where it started, correct? But what has happened, this atom has absorbed energy from the incoming X-ray, from that initial incident photon, and it has produced two brand new, lower energy, slightly poorer photons in return. Does that make sense?
Yeah.
So that is the idea of photoelectric interactions or photoelectric absorption. High energy X-ray comes in, hits the inside takes all of the energy, so no more photon, and an electron decides to wander off. Leaves room inside the atom, the other electrons start to jump down. Every time they jump down, they now need to give energy out into the environment. They have to pay the environment some energy.
But it's less energy each time.
But it is less energy. And so you're gonna have these really low energy photons coming off the atom now. And those are gonna be those secondary photons. Okay, not scattered, right? This is not
Still,
scattered.
it's not the scatter.
This is not scattered. Right? These are just secondary photons.
So basically, I just wanna make sure I got this right in the middle. Okay, so an X-ray, an X-ray photon hits the inner shell, right? Electrons, and then it's removed from the atom. The outer shell electrons move into the inner shell to fill up the space of the gap, right? As they change shells, energy is released in the form of an X-ray, right? And then so that's known as characteristic radiation, and is a secondary radiation, right?
Correct.
Okay. Okay, I was making sure that.
So the
I
first one
understood
you
that. So
described
that's
was-
when, I'm sorry, that's when the money exchanged hands, the photon energy exchanged with the electron, knocked it out. Then created another little energy on the outside, which is a new photon that changed hands. It changed energy with that atom, which was J, and then knocked it out. And
Very
then- Okay, I was making sure, I'm following you.
Yes.
So what I was thinking that now this atom, this energy, the photon is going to come and hit it, right? The electron in the atom. But why does it want to come and hit the electron in the atom?
It doesn't want to, it just happens. Right? For example, if I took this remote and just threw it, it's not like I want to win, but it just so happens that she's in my way, right? So it's gonna hit her.
Then
Sorry.
Get that energy, girl.
Right? So the X-ray comes out of the tube, it doesn't intend to hit anything, it's just going in a straight line. If there's something in its way, then too bad. that thing is going to get hit.
Right.
Okay?
So this photon is the X-ray that's coming out of the tube, so the first one.
The first one, yes.
It is like is the tube that's giving that all that thing happening in the filament and everything, and that the one that is coming out is the photon,
Correct.
and that photon might hit a few electrons on the way.
Correct.
But if it doesn't hit, it will go on its way straight.
Right. So if that photon did not hit anything, right? If it passed through the patient without hitting anything at all, what is that called? Transmission. Okay?
Oh, the photon doesn't hit any matter inside the person.
That
That's
is
not
good.
possible, right, sir?
That's transmission.
That's
Yes.
not possible, right, sir?
It is
Because
possible. We have transmission. We have a
the
lot of
photon
transmission.
can go through people without hitting the atoms?
Yes, it will.
Oh.
And then it
Okay,
goes
so
scatter.
this that we demonstrated just here with photoelectric, where the photon disappears. What is that called?
Absorption.
Absorption. So always associate photoelectric with absorption. Right? In fact, some textbooks even call it photoelectric absorption rather than just photoelectric interactions. And then we have the third type of interaction. What is that? If it's not transmission, if it's not absorption, what else can happen?
Then it's the scatter, sir.
Great. Then we have scatter.
Scatter.
Absorption and scatter. What can we group both of these under? What is the big category for both absorption and scatter? The
Big
fancy
two.
word. Fancy word that was up here.
Attenuation.
Attenuation.
Ah.
Yes, that is the fancy word.
Absorption plus
For absorption and scatter. Anything which is not transmission is attenuation.
absorption and
Anything that is not transmission is attenuation.
scatter.
All right, great. That's it. Thank you. Thank you.
Then-
So if you want, you can keep the money. Otherwise, just pass it back to me. I'll bring Monopoly money next time or something.
Yeah, I get it now. When I get home, I think about it, and I had to read the book again.
Well, charges are kind of, a lot of them are so similar, like, I'm trying to think. Like on one of them, it's just because it moves
So
really
in the
slow,
atom
like
instead of
plastic or
gravity,
whatever, just.
we have
moves it so
electrostatic
much.
forces. So remember, inside of the atom, there's a proton, positive. Electrons are attracted to protons. So that's why we want to chromium to us. So remember,
I have to really go home and take a look at it.
Yes.
I have this there. My mind be going. Cause if it's ugly, I'm going, trying to look through it, I rewrite it pretty. But,
What's transmission?
Transmission is whenever it gets like nothing is
So
absorbed, but everything is
photon
passed through.
comes in, hits the electron
You
in the
mentioned
atom,
a
no
book
more
example.
photon. There's no
That's
direction
what I was
change.
asking
That's
because
gone.
that made more sense to me than what
So
we
there's no
did.
direction change because the photon just
If
vanishes.
but I have it.
let's say you have 6
So,
books
yep, photon
starting,
loses
pull
all the
the
energy.
bottommost book, that's
and
the
it's gone.
incident. That's the
The
that's the
photon
one.
loses
That's
all
why I
energy.
put it on
You
and
pull
stop.
that bottommost book, electrostatic forces or gravity
electron
pulls
here,
those books down.
This one leaves.
But since there are 6 to
Direction
start, there's a
doesn't
set
matter.
amount
All we know is
of
that-
force that's the initial.
That's why I
This
got
is-
it.
Pull out another book, it's gonna hit the table,
So-
not as hard. It's still gonna hit the table.
When it leaves,
So that
yes, you're
sound
gonna have
is
a,
that less
it's gonna be
energy, right?
characteristic.
And then when you take another book, it's even less energy, but you're still removing a thing, you know what I'm saying? So, you got 3 photons.
So, are you talking about the photon or the electron?
Yeah, essentially.
The electrons which drop down, I don't believe
So
I've
he
given them a
said
name.
if it's scatter or
Scatter or absorption. If it's
not absorbed, that's attenuation.
Yeah. No.
Not absorbed, not.
Yeah, yeah.
I remember seeing that in the book.
So when you said anything that is not, anything that is absorbed and anything that is not a scatter is attenuation, right?
not scattered.
Scatter is attenuation.
Anything that is not a scatter, anything that is not scatter is attenuation.
Anything that is not transmission is attenuation. Anything that is not transmission is attenuation.
So scattered
So
can be.
anything that.
Scatter is attenuation. Absorption is attenuation. Correct. Anything that is not transmission is attenuation. Basically, if I have 100 X-rays leaving my X-ray tube, I expect 100 X-rays at my detector. Anything that causes me to have less than 100 X-rays reaching the detector is attenuation. Why would I have less than my full amount reaching the detector? Well, the X-ray can not reaching the detector. The X-ray can come in here, bounce off, go somewhere else. Now I only have 98 reaching the detector. So attenuation is anything that keeps me from getting all my X-rays to the detector. Right? So absorption and scatter are the reasons why the X-rays will not all reach the detector. Does that make sense? All right, great. Starting is a good point, is a great point to be at. Okay. Any other questions here? Okay. So, in that case, let's talk about how we can measure the amount of radiation. So, these are going to be very important units to know.
Is this page 36?
Let me take a look.
99.
It's like 90.
I meant in the PowerPoint because that's what I think we wrote over here.
And that's what taking this.
Slide
43.
43.
43. Okay.
It's in the big
Then I don't know
one.
what else. Was that Shepherd or?
Wait.
100 if you're in the book.
Like a couple
Page
of
100
pages.
if you're in the book. So,
It was on
It was
for
my
CES.
handwriting, bro. Why do I keep seeing it?
okay, we have, remember, in this world, we currently have two major ways that we can measure things. We have traditional units, and we have the international system, the SI system. Right? Traditional units are going to be your feet and your inches, right? They're going to be your miles. They're going to be your gallons, your cups, your quarts. Right? International system, SI system, right? Metric system. This is going to be your meters. This is going to be your kilometers, your centimeters. This is your liters, milliliters, right? So, we have traditional units, we have SI units. In science, we prefer to use SI units. So these are the ones that we're mainly going to be focusing on. But every SI unit has an equivalent traditional unit. Okay? Every SI unit does have a equivalent traditional unit. So at the very least, I do want you to kind of recognize the traditional units, kind of be familiar with which SI units they match up with. But if we do any math, our math is going to be in SI units. Right? If I give you any numbers, for example, any dose measurements that you need to memorize, those would be in SI units. Right? So eventually, when we talk about things like occupational dose limits, how much radiation are you allowed to get before they say, no, you can't work in a radiation area anymore, right? Those are going to be based on SI units, not traditional units. You can always convert if you want, but we're not going to worry too much about them.
So I have a question. You said traditional units for feet and inches, and this is rad and rem and curie.
Yes, so traditional, right? Traditional units, as an example, right? American units, right? America uses feet and inches, right? Most of the other world uses meters and centimeters, right? America uses gallons. Most of the world uses liters, right? So traditional units are those old style, English style, American style units. International system those are the more scientific style units that we use. Right? Traditional units, things like horsepower versus newtons and joules. So, as you may notice, over here for traditional units, we have the Röntgen, which is named after, as you may guess,
Founder of
Wilhelm Röntgen, yes, the discoverer of X-rays.
November 8, 1895.
November 8th. Very good.
Get it, girl.
Okay, we have the RAD, we have the REM, we have the Curie. Over here on the international side, the SI units, metric system, we have coulombs per kilogram. Right? Once again, right? In traditional, you have pounds, right? SI system, you have grams. Over here, we have the Gray, the Sievert, and the Becquerel.
So the columns in kilogram, so it's the traditional use Röntgen in some places.
Oh,
It's comparing with that, sir.
yes, it is. So, if we are talking about exposure, about ionization in air, we will be using either Röntgens, if we're traditional, or coulombs per kilogram, if we're using the SI system. Okay, so we have Röntgens, which is measuring the same thing as coulombs per kilogram. This measures ionizations in the air. Remember, X-rays are ionizing radiation. They can ionize particles inside your body. They can also ionize molecules in the air. So we can measure the amount of ionization happening in the air, and that is going to be our coulombs per kilogram. Okay. So, a coulomb is a way to measure charge. Right? So a coulomb is a way for us to measure charge. So by saying coulombs per kilogram, we're saying how much charge, how many charged particles are we creating for a kilogram worth of air? Does that make sense? The more X-rays you have, the more charged particles you will create. So this is a way for us to measure the amount of radiation. The more coulombs per kilogram, the more charged particles we have for a certain amount of air, then that means there are more X-rays, more radiation, more dose. Okay? So that is our first way to try and measure the amount of radiation. Now, note that this does not indicate actual exposure to individuals when they absorb radiation, right? This is talking about exposure in the air, not exposure inside tissue. If we want to talk about tissue, if we want to talk about ourselves, we need to use a different unit. That unit is the rad for traditional, or the gray for SI. So we have rad, radiation absorbed dose, which is also called the gray in SI units. Gray is what you're mainly going to be seeing, either gray or milligray. Okay, remember the prefix milli means 1,000th. So a milligray is 1,000th of a gray. Bless you. You would have 1,000 milligrays inside one gray. If you were to take a gray and break it down into its component units, it is actually joules per kilogram. Joules are a measure of energy. Kilograms are a measure of mass. So this is saying that you have this much energy going into this much mass of tissue. Right? So if you have this much mass of tissue, you will have this much energy being transferred into the tissue. So that is how we describe dose. The transfer of energy from the X-ray photons into the tissues. the more energy that gets transferred, right, the more energy that gets absorbed, then the higher the dose will be. Does that make sense? Right? If your body absorbs more X-rays, then naturally your dose is going to be higher. So this is the amount of energy being absorbed dose. Right? Makes sense. Easy way to remember this. What does absorb start with?
A.
Okay, what letter do you see here in rad? What letter do you see here in gray? A. So your rads or your grays are your absorbed dose because they have the A. Now compare this with equivalent dose. This is another way to measure the amount of dose inside the patient. Traditionally, we call this radiation equivalent man, the REM. But now, we call it the sievert. So the SI unit is the sievert. This is the one we will mainly be using. Once again, you can use sieverts or we can use millisieverts. Just like we can use grays and we can use milligrays. The sievert is based off the gray. It is based off the gray using something called the quality factor. This quality factor is determined based on the type of energy. Because not all energy is made equal. Not all ionizing energy, not all ionizing particles are created equal. There are some things which ionize, which are more dangerous than others. And that is why we need to be able to account for that change in danger. So, for X-rays, gamma rays, or beta particles, which we'll talk about later, main thing here, right, X-rays, they have a quality factor of 1. So if we have 10 grays, and our quality factor is 1, how many sieverts would that be? 10 grays
10.
multiplied by a quality factor of 1 gives us
10 C.
10 sieverts. So when we are using X-rays, right, which we will be, the grays, 10 grays, will be equal to the sieverts, 10 sieverts. Okay, nice and easy. Right? Transfer straight across. Change the unit. But sometimes things aren't that nice. For example, we have alpha particles. These bad boys are made of 2 protons, 2 neutrons. They're giant particles in the atomic world. When they interact with the atom, they cause big changes. So the amount of effect an alpha particle has would be 20 times the effect of an X-ray. So the quality factor is 20. Which means for every 1 gray of alpha particle radiation, how many sieverts would that be?
20.
20 sieverts. Right? 1 gray, 20 quality factor, 1 times 20 gives you 20 sieverts. If it was 5 grays, what would be the number of sieverts?
100.
Good, 5 times 20, so 100 sieverts. So 5 grays of alpha particles would be 100 sieverts worth of alpha particles, right? The quality factor changes the amount of dose, the dose equivalent. Does that make sense? Because alpha particles are just so much more dangerous because so many more issues compared to X-rays. Now, easy way to remember these units. What does equivalent dose start with? E. What do you see in REM? What do you see in sievert? E. So the units with an E are your equivalent doses. Okay, units with an A are absorbed, Units with an E are equivalent. Does that make sense?
So you said quality factor changes what, sir?
Quality factor is,
You said the quality factor changes something.
oh, I don't remember my exact words anymore.
So
You might need to check with Samantha.
what is quality? Oh, I didn't have a recording. But what is the quality factor
She
change?
forgot to press record.
Quality factor changes the amount of dose,
The amount of dose. Yes,
right?
that's
So
right.
you have a low absorbed dose, but you have a high equivalent dose because of the quality factor. Quality factor tells you how dangerous or how much more dangerous that type of radiation is, right? It tells you how much more dangerous alpha particles are compared to X-rays, or how much more dangerous neutrons are compared to X-rays.
Makes sense.
So, when you do get dosimetry readings, for example, when you do get your dose reports, they will be in either grays or sieverts, right? With X-rays, it's the same thing, right? Grays and sieverts, same number, right? And they'll tell you how much dose was absorbed in the tissues. Now, we have another unit that we need to keep track of, which is air kerma. Does anyone know what kerma means? Have you seen that word before?
Just to research kinetic energy radiation.
All right, that's right. So it's not actually a word. Kerma is actually an abbreviation. Kerma stands for kinetic energy released to matter, or released in matter. So basically, it's how much energy is transferred to matter. Well, remember, energy is joules. Remember, matter is kilograms. So kerma is measured in joules per kilogram, which is the same as a gray, right? We just saw that 2 slides ago. Grays are joules per kilogram. So air kerma is also measured in grays. This is, once again, talking about energy in air. That's why it's called air kerma, right? Energy released in air. So 1 air kerma, you release 1 joule of energy inside 1 kilogram of air. This is a way for us to measure things like scatter. It's a way for us to measure things like entrance dose at the skin. Okay, so this is a very common thing we use. Sometimes we take kerma and we combine it with the area being exposed, and then we have like a kerma per area, or kerma over the area. Okay, so this is air kerma. It's a way to measure radiation in air. And this has basically replaced the Röntgen, or the coulombs per kilogram we saw earlier. Both of them measure air exposure. And our final unit that we will talk about today is radioactivity, radionuclide decay. So the old school unit was the Curie, new school unit we call it the Becquerel. This is the rate at which a radionuclide decays. So if you've got a lump of uranium, and the uranium is decaying, right? We can measure how quickly it's undergoing decay using these units.
So what's a radionuclide?
A radionuclide. So this part, nuclei, refers to the nucleus of an atom. Radio means that it is radioactive. It undergoes radioactive decay. So what that means is, you've got the nucleus of an atom. It's got protons, it's got neutrons inside it. But there are so many things inside this nucleus, it's not very stable. It doesn't like the way it is. It's too crowded. And so eventually, the nucleus decides, you know what? I'm sick and tired of all these people here. I'm kicking some people out of my house. And so the nucleus goes, it opens the door, and it kicks someone out of the house. Just like that, right? Kicks someone out of the house. Just, you. And that is decay. When it kicks someone out of the house, it turns into a new atom, which is hopefully more stable.
The one that is kicked out is the new atom, sir.
So the house is now new.
A new atom.
And the house is now new. Right? This particle which leaves, it can be a beta particle, it can be an alpha particle, it can be a neutron, doesn't matter. Doesn't matter. The idea though is that something is getting kicked out, and so now the nucleus here has changed, fewer stuff, fewer people inside, and now it is more stable, it feels happier. Until it decides that it's tired of all these people and kicks someone else out. So, how quickly this happens, how many of these nuclei are kicking things out, that is measured by the becquerel. So, for example, if out of our sample, right, we've got 100 nuclei kicking things out of them per second, right? That would be 100 becquerel, right? We'd have 100 disintegrations, 100 of these decays going on per second. So it's just a way to measure how often, how radioactive a substance is. The more radioactive, the more often it is kicking things out, and the more particles it is producing. Remember, particles it produces are radioactive particles. It's creating gamma rays, and it's creating alpha particles or beta particles or neutrons. Now, why is this important? I mean, we're working with X-ray. We're not working in a nuclear power plant. We're not working with nuclear weapons. Why do we need to know about the decay of radioactive materials if we're in X-ray?
Because they affect our tissues, sir. They absorb radiation.
Sure, but I mean, do we see radioactive materials when working in X-ray or in medicine? Yes.
No.
In nuclear medicine, very good. We do work with radionuclides in nuclear medicine. We give patients radioactive material to ingest so that we can follow the path of those radioactive materials. We can see where they go in the body. For example, if we are doing a stress test, we can see which parts of the body are using up the most oxygen by following those radioactive particles and imaging them. Right? And so, why are those particles radioactive? Right? They're undergoing this radionuclide decay. And these particles, this energy which is being released, that is what we are imaging. So, this is important for nuclear medicine. Right. Any question over these 5 units? Once again, as far as the SI versions go, we have exposure in air, which is coulombs per kilogram. Absorbed dose, which is our gray. Equivalent dose, which is our sievert. Our air karma, which is also gray. And then finally, radioactivity, which is the becquerel. These are the 5 units you need to know.
Both the traditional names, and as far as the names go, the traditional names also.
Traditional names, be able to match them with your SI names. Yes.
So this is similar to like half-life in chemistry and whatnot?
Similar to half-life, yes. Well, half-life looks at how long it takes for half of something to decay. This is looking at disintegrations per second. But 2 ways of measuring something very similar. Cool. Okay. Now, of course, we don't just let anyone handle radiation. So, there are more agencies that we need to know about. which do this regulation of radiation. Yes, I know, more agencies. More agencies, I know. You thought you were done with JSER and ERRT and all that, but we've got a few more that we have to cover. Okay. For example, when dealing with equipment, we have the Center for Devices in Radiological Health, right? Devices, therefore equipment, CDRH. Right? This CDRH falls under the jurisdiction of the FDA. Right? So the FDA uses the CDRH to set standards for equipment. Okay, we have the NCRP. This one is pretty important. NCRP, the National Council on Radiation Protection and Measurement. You will be seeing these again next year. You will be seeing the NCRP again next year. They give recommendations, but they do not enforce the recommendations. They leave it to other agencies to create the laws and the enforcement for those laws. The NCRP only looks at the research and gives recommendations on what it thinks we should do to be safer. NRC, Nuclear Regulatory Committee. So these are the ones that take those recommendations from the NCRP and they use them to create and enforce regulations. Okay. So NCRP gives recommendations, NRC creates actual regulations based off them and then enforces them. Right. So, for example, right, Dr. Black gives us, the instructors, recommendations on what we should be doing. We as instructors are the ones that actually take his recommendations, put them into practice, and then try and enforce them.
And NRC will take it and use it in practice.
Correct.
NRC.
All right, those limits. Do you need to memorize this chart here on the right?
No, so we can look at it, sir, I suppose. We did carry
Yes,
one.
you will need to memorize that chart eventually.
Oh, I see.
You do not need to know this chart for the semester. But it is here for you to look at. If you want to get a head start, feel free to turn these into flashcards. But you do not need to know these right now. Okay? You do not need to know the chart right now. Next year, yes, you will need to know this chart. So if you want to study it ahead, get a head start, then great. You will be prepared by this time next year. So, the main thing here on the slide though is this concept of dose limits. Right? So the dose limit is something that is set by the government or set by the agencies, and this is the maximum permissible dose of ionizing radiation that we believe carries a negligible risk of significant bodily or genetic damage. So notice that it does not say no risk, correct? What does negligible mean?
Which can be ignored, sir, it won't affect you.
Can be ignored. It probably will not affect you. For example, if I buy a lottery ticket right now for that, what is it now, like
$2.
$800 million jackpot or something? Right?
It's for $2.
Come buy one when I come out.
Right? If I buy a single lottery ticket, right? What are my chances of winning?
Negligible.
Negligible. Do I have a chance of winning and then quitting this job and retiring to the Bahamas? Yes, maybe. But I'm probably not going to, right? I'm probably going to be here again next week. I'm probably going to be here next month because I'm probably not going to win the lottery.
So is it safe to say you're not here? You run off.
I'm not going to say that. So, with radiation, same thing, except this time it's the lottery for bad things. Right? In radiation, right, you get hit by an X-ray, that's like pulling a lottery ticket. If you win the lottery, then you get cancer. Congratulations. Okay, it's the lottery for bad things happening. But what's the chance of you actually getting cancer from the X-rays? Negligible. Very low, probably not going to happen. As long as you stay below the dose limit. Does that make sense? So this is the dose limit which we have decided, right, based on research, based on studies, based on evidence. This is the amount of radiation we have decided is acceptable without causing a significant increase in the chance of damage. Above the dose limit, then yes, now we're getting into a region where you're more likely and more likely and more likely to see effects. Yes, Emily.
So once you pass the limit, do they recommend like retiring or taking out or?
So usually these are going to be annual dose limits, so they will remove you from the radiation area for the remainder of the year. Which is going to be rough if your job is working with radiation. Because what are you going to do if you can't work in an X-ray room? MRI, okay. Great. Come back in 2 years and we can work on that. So, you'll notice that for your dose limits, it is different for depending on what we're looking at, right? We do have an annual dose limit. The annual dose limit is what?
50 millis.
Good, 50 millisieverts. Okay, SV is sieverts. Your cumulative effective dose limit. So this is your lifetime dose limit. What is that?
10 millisievert multiplied by your age.
Right, 10 millisieverts multiplied by your age.
Sieverts, sir. Oh, sorry, sir.
Sieverts.
Sieverts.
So if I'm 30, then my cumulative effective dose limit
Is
would be
33,000.
300.
3,300.
300, yes. If I was 60,
600.
600, right? So that would be my lifetime dose limit. So that means that maybe some years I can get less, some years I can get more, but overall, I would also want to stay below my annual and cumulative dose limits. All right, keep in.
If they ask you to leave, after that annual, do you come back next year and it restarts?
Yeah, I mean, as long as you haven't also gone over your cumulative, then yes, you can come back. As long as they also haven't fired you. Yeah, you can come back.
So,
That I don't know. I've never seen that happen to anyone. Because 50 millisieverts is actually really, really, really high for a dose limit. No one working with X-ray should come close to approaching 50 millisieverts, unless they themselves were sitting in the middle of a CT scan. The CT scanner is scanning themselves every single day. You should not approach your 50 millisieverts.
when it says cumulative in a year, and if you're 50 years old, it should be 500 millisieverts.
Correct.
So that means if I'm 50 and it's already 500 millisievert, then I should not be going anymore to do X-rays because I might live another 10 years or something.
So,
Or 40.
if you're, let's say that you're 50 years old, and that you've received 500 millisieverts
Yes,
of
that's what my
radiation.
question is.
When you turn 51, now your dose limit is 510. So now you can gain an additional 10 millisieverts without going over your dose limit. But your dose limit has changed. So then you can go back and work as long as you don't go over
Oh,
an
I see,
additional.
because it matters, it changes with the age, right? So because
Correct.
it will oh, I see.
Of course, once again, that should never happen unless something has gone horribly wrong. You take a look here, right? We can also change those. We also have dose limits based on the body part, right? Eyes, hands, things like that. And then you notice that this is occupational dose limits for people working with X-rays. People who do not work with X-rays, the public, have different dose limits as well. Okay, so there are going to be a lot of considerations as far as dose limits go. Right? You have your adult population, you have your fetal population. So, it does depend on a lot of different factors what the dose limit is going to be. Okay, so this is something that you will need to know next semester.
So what are you supposed to know here? What is this effective dose limit for an occupational exposure? We should know that. What is annual dose limit for an occupational exposure?
Are you asking about right now?
No,
What you need
no,
to know?
like it said, like for if I have to learn something, remember this. What am I supposed to remember? That I should know. I, as a technician, as a technologist, should know the dose limit for.
You should know all these dose limits. You should know all these dose limits, so when you get your dose report, you know what you're looking at. You should know these dose limits, so if a patient asks you about doses, you can answer them with knowledge. But you don't need to quote all the numbers for the patients, but you can explain to the patient like what a dose limit is, or you can explain to them how much dose you're getting from an X-ray. Right? You want to be knowledgeable, you want to be the expert, the subject matter expert, if you are asked about this, right? If the doctor asks you about it, because right, doctors don't really learn this in much detail, right? If the doctor asks you, you should have enough knowledge to be able to answer them.
It would be wrong to take out a card from this.
You can take out a card and answer them. Yeah, sure, why not? If you want to give them accurate information, it might not make them feel very
Because to
confident.
have that on memory might not be.
Whatever you want, right? At that point, it's your license, it's your job. Right? At that point, I can't tell you what to do. You do whatever you think
So,
is
but then
best.
my question to you then again is, because I might have placed my question wrong, that I must know this by memory. I should try and learn these levels, know them by memory, sir.
For the exam, for the registry, yes, memorize this entire chart. Will you need to know it for this class? No. Will you need to know it for radiobiology or radiation protection in the fall? Next year? Yes. Okay? So this will show up in semester 5. I'm not going to ask you to memorize it for the class now, but you have to know it for semester 5. You have to know it for your exam.
I see.
Do you know how much you've been exposed to?
Usually when I get my report, it says unable to detect. So I got such little exposure that not even the monitor here was able to detect how much I received.
So
Right,
we
so
should
very
be
low levels.
we should be within those very low levels.
Correct. The only time I expect it to be measurable is if you're constantly working in fluoro, if you're constantly working in IR, or constantly working in OR, places that are higher radiation levels. Okay. And remember, this all comes back to ALARA, right? As low as reasonably achievable for our doses. Even though these are the dose limits, we never want to come close to reaching them. So you keep things as low as reasonably achievable. All right. Now, we're going to kind of switch from physics to biology here. Real quick refresher. This is a cell. Humans are made of cells. Humans are made of a lot of cells. That's why we are multicellular, right? Lots of cells. Cells themselves have a very basic structure. On the outside, they have a cell membrane. That is kind of the thing that, the walls of the cell that enclose the cell. It's like the outside of a balloon. Inside is the cytoplasm. If this is a water balloon, then it's the water inside the balloon. Inside there is the nuclear membrane. It's like if you took a second water balloon and snuck it inside the first one. Okay. And inside that nuclear membrane encloses the nucleus. The nucleus is important because it is basically the center of the cell, both literally and figuratively. The nucleus contains the important information necessary for the cell to survive and to function. It contains the DNA of the cell. Remember, DNA acts like the cell's blueprints. It acts like the cell's instructions. Now, there are two types of cells. We have somatic cells, which are the body cells. So skin cells, nerve cells, stomach cells, liver cells, muscle cells. Those are all somatic cells, cells of your own body. But we also have germ cells. Germ cells are the reproductive cells. Right? For males, that would be the spermatogonia. For females, those would be the eggs, the oocytes. Okay? So you have the sperm and you have the egg. Those are the germ cells. They are used for reproduction. Radiation affects them slightly differently. When a cell is exposed to radiation, there are two ways it can take damage. Number one, you've got a strand of DNA. X-ray comes along, and with pinpoint sniper accuracy, it hits the DNA and breaks the DNA. Okay. So that is called direct hit. If the radiation hits a structure like DNA, it will damage it and cause changes. However, where is the DNA kept in the cell?
In the nucleus.
In the nucleus. Right? Chromosomes, nucleus, good. Stored as chromosomes in the nucleus. Okay. Is DNA a very big structure? No, not really. It's really compact, squeezed into a really tiny space in the cell. So, a lot of times, it's very hard to land a direct hit on DNA. So direct hit is usually not going to be the main source of damage because there's very little DNA in the cell to actually target. Instead, the cell will take damage from indirect hit. So the radiation interacts with the cell's cytoplasm. Remember, we said the cytoplasm is like the water in a water balloon, right? So it interacts with the water inside the cell. What is water? H2O, yes, great, H2O. Very famous, right? 2 hydrogens, 1 oxygen. X-rays are what kind of radiation?
Ionizing radiation.
Ionizing radiation. So what happens is the X-ray comes along, it runs into the water molecule, and it ionizes it. It strips off an electron. And now the water molecule is unstable. It's unhappy. It's like, I want my electron back. But it's like you took away a toy from a kid. It wants it back. And it will do anything it can to reclaim its electron. In fact, it will go so far as to try and steal electrons from other molecules to get back its electron. And when that happens, when 2 molecules or 2 atoms start to take electrons from each other, you form chemical bonds. So that water forms a chemical bond, creates a chemical reaction, and suddenly you have something that's not water. You have something which is H2O2 instead of just H2O. You have H2O2.
Hydrogen peroxide.
Hydrogen peroxide, yes. So, what do you drink water? Who is willing to drink water? None of you? Are you all soda drinkers? Like, what's going on here?
Just straight ethanol here.
All right.
You get lit.
All right, who wants to drink hydrogen peroxide?
Not me.
Why not? It's just the nature of oxygen. Oxygen's good for you, right?
It's a new chemical, and hydrogen peroxide absorbs actually.
It kills the germ.
It's gonna destroy
It's
your blood.
it absorbs something. I don't know.
Right. Hydrogen peroxide is toxic, right? It destroys cells. It destroys bacteria, germs, but it can also destroy your own cells. So when X-rays hit the water inside the cell, it can produce hydrogen peroxide within the cell. Right. That is toxic to the cell.
So sorry, I didn't understand, sir. But what happens inside the cell to hydrogen peroxide, sir?
So the X-rays hit the water, and they can convert the water into hydrogen peroxide.
Inside the cell. Oh, I
Inside the
see.
cell. So now you've turned some of the water in the cell into hydrogen peroxide.
That happens in indirect.
That happens in indirect. Right? So we're not directly interacting with the DNA anymore. We're interacting with the stuff around the DNA in the rest of the cell.
And that's when it hits the cytoplasm.
When it hits the cytoplasm.
And this water is in the cytoplasm, sir.
the water, yes, the liquid of the cytoplasm. That's right.
Oh, so once that becomes toxic, then it will attack the chromosomes also.
Right, so,
Oh, I see.
right, hydrogen peroxide toxic to the cells. In addition, have you heard of free radicals?
Yes.
Not
Right.
me.
So free radicals, they're highly reactive elements, they're very bad for you. Right? That's why they always say eat your antioxidants, right? Eat your blueberries or whatever, to help get rid of your free radicals. Right? It's true, free radicals are bad, they are carcinogenic. What happens is the free radicals want to interact with things. They will interact with whatever they can get their hands on. If it's water, they will interact with water to create hydrogen peroxide. However, if the free radicals get near DNA, they will interact with the DNA and cause damage. So you can indirectly damage your DNA due to interactions with cytoplasm. X-rays reach the water in the cytoplasm, it creates free radicals, and the free radicals attack the DNA. So direct hit, X-rays directly hit the DNA. Indirect hit, X-rays hit something else. And the something else then interacts with the DNA.
But sir, you said it never hits directly, right? Because the DNA is so small.
It will,
It
It
can
will.
hit it directly as well.
but not often. It's not easy to hit it directly. Right, for example, right, once again, right, got some markers, right? If I just start trying to throw it at Samantha's camera there because I don't like her filming me, right? Chances are that it's going to be really hard for me to actually hit that camera. But I might hit the people around her, which are then going to like go ouch, swing their arms up and hit the camera for me. So that is direct versus direct. A few of these will hit the camera. Most of them are going to hit someone else instead because my aim's just not very good.
What was indirect again?
You mean a J and he falls back on the
So
camera.
X-rays hit the water, X-rays hit the cytoplasm in the cell. It creates bad substances, those bad substances attack the DNA. So in the end, it all comes down to DNA, doesn't it? It all comes down to DNA. And that is target theory. Target theory says that if you damage common molecules, not much bad will happen to the cell because the cell can replace those molecules or repair those molecules. But if there's a very important molecule that gets hit, that is going to have some major effects, correct? Okay. So, for example, if tomorrow I was walking down the street, I fell down a manhole, and I got stuck and could not come into work for the next month, that would have some effect to you guys, correct? On the other hand, if, let's say, President Biden was walking down the street, he fell down and got stuck in the manhole for 1 month, that would have much bigger effects, wouldn't it? Right? Because the importance of me versus, like, President Biden are very different. Same thing, target theory. You have a common molecule that gets hit, no big deal. There's thousands, millions more just like it. DNA gets hit, oh, okay, now we're in trouble. Because this is a very important, a very critical molecule for the cell survival. So that is the idea of target theory. Does that make sense? All right.
Maybe a better example would be, sir, like the class,
Mhm.
and if something happens to me, nothing happens to the class. But if something happens to you, then the class is in trouble.
That's true, but I didn't want to hurt any of you in my I mean, I don't mean to hurt President Biden either, but I'm sure that's going to be taken care of. He'll be taken care of.
He'll be alright.
He'll be okay.
He's doing just fine on his own.
That's true. That's true. That was insensitive of me.
That's
so-
security and stuff too.
Okay. So let's talk about what cells are more sensitive to radiation. Okay. The cells which we will see the biggest effects in are the ones that will undergo rapid division. Right? Remember, that's called mitosis, cell division. Okay. So the old idea was that cells that do mitosis are more sensitive. Right? Nowadays, we prefer to think of it more like cells have the same sensitivity, but the effects are more obvious when they divide rapidly. Right? So it's not that nerve cells are naturally more resistant to radiation than sperm cells. It's just that because sperm cells divide so much more, you see the effects a lot more compared to with a nerve cell. Does that make sense?
So in meiosis, it is more rapid than mitosis.
What?
That's it.
No, mitosis. We're not talking about mitosis and meiosis at all. All we're saying is that the more often a cell divides, whether it's mitosis or meiosis, doesn't matter. But the more often it divides, the more you will see the effect. Right? So instead of saying sperm cell, maybe I could have said muscle cell. Right? Muscle cells divide more, or skin cells, they divide more than nerve cells do. So you would see the effects more readily in a skin cell versus a nerve cell. And you'll see that as well when we start talking about radiobiology, because you notice that the dose limits required to cause skin reactions are much lower than the dose limits required to cause reactions in the nervous system. Yes?
And this is like why we don't X-ray women who are pregnant or whatever they have issues, because it might cause them harm to those cells or whatever that are like in those division processes, right?
Correct. Because with an embryo, with a fetus, those cells are dividing very, very quickly. Right? And so because of that, if they are radiated, you will see the effects of that radiation much, much more. Okay? So it deals with the speed of cell division. And then that also kind of goes into cell specificity, how mature the cells are. But don't worry too much about that yet. Okay, if exposed, what could happen to the cell? Well, actually, most cells, when exposed to radiation, they just repair the damage. They shrug it off, they repair it, they go on their way, no problem. But in some cases, right, the unlucky cells, the ones that won the unlucky lottery, those cells may die before they are able to divide again. They may have slower cell division. Okay, so you are going to be looking at some changes to how the cells behave occasionally. Most will repair themselves, but some of them will show changes. Right.
So it was die, delay mitosis, and what was that thing, sir?
Or repair themselves. Okay, so I'm going to try and go through this really quickly. There are two types of response to radiation. Early, which is like acute, and then late. So early is something you see almost immediately after exposure, like within days, hours, days, weeks after exposure. Right? Acute radiation syndrome is an example of this. We do have some stages here, right? So after you're exposed to radiation, you go through prodromal stage. Afterwards, you go into the latent period. Afterwards, you go into the manifest stage. Basically, what all this means, prodromal stage, you have some initial symptoms of radiation poisoning. Nausea, vomiting, diarrhea. But then, those symptoms go away. You look healthy again. But you're not actually healthy. Inside your body, changes are happening. And when those changes finally finish taking place, you hit the manifest stage. And this is when the worst stuff happens. Okay? During the manifest stage, treatment will determine whether or not you enter recovery, you live, or you enter death, which is you die. Okay? So, those are the stages of your early term effects to radiation. Now, let's say that you got exposed to radiation, but not enough to go through this. Or let's say you did go through this, but you survived. You are not out of the woods yet, because we have late-term effects, long-term effects, somatic effects, effects of the radiation which only affect you as an individual. So if I get cancer because of the radiation, I'm not going to pass the cancer down to my kids, right? The cancer will only affect myself. That is a somatic effect. And cancer is a long-term effect. If I get cataracts, same thing, it's only going to affect me. Genetic changes that affect my future descendants. So in this case, if my sperm were irradiated, and then there were mutations, there were changes, and then I passed those down, those would be genetic effects. So birth deformities, like birth defects, or changes to the chromosomes, right? Genetic diseases caused by radiation, those would fall under genetic effects. Right? Because that's not only affecting me now, that is affecting my future offspring. Yes?
If a patient fears they might be affected genetically, they would go through genetic testing to see like how they've been affected, or okay.
Yes, they could. Very good. All right. How much more do I have here? All right. Okay, that took a little bit longer than expected. All right. So in that case, we'll have to leave off here. On Friday, we'll finish up this chapter by talking about radiation protection, and we will move on to chapter 10. Chapter 10 is about diversity. Okay, so make sure to look over that chapter as well. Any final questions before we finish?
Can you go to the last slide real quick, please?
Our test is next Wednesday.
So right now it looks like we are going to need to push everything back one day on the schedule again. So I'm going to make the change to the syllabus. I will send out an updated syllabus with all new dates, okay? So please keep an eye out for your emails to look for that new syllabus. Make sure to replace your old syllabus with the new syllabus. You'll see you next time.